Ethics for critical AI systems. What happens when intelligent agents move from simple automation into critical, real-world decisions? You can see their impact across healthcare, finance, smart systems, and other complex environments. You can also see why ethics, performance, and system design must be considered together. This exploration focuses on 4 connected areas. It covers advanced agent systems, industry applications, ethical considerations in agent-based computing, and ways to improve agent-based systems in real-world environments. Together, these areas show both the promise and the challenges of intelligent agents. In healthcare, agents support patient monitoring, diagnosis, medical device coordination, and disease spread simulation for pandemic planning. One example is real-time monitoring of intensive care patients, where agents analyze patient data and alert providers about critical conditions. In smart cities, agents help coordinate vehicles, manage energy distribution, and model urban behavior. In financial markets, agents are used for algorithmic trading and risk management through market simulations. One example is trading bots using reinforcement learning to identify profitable patterns in stock markets. In environmental science, agent-based models can represent ecosystems, species interactions, and climate-related effects on biodiversity. In defense and security, agents support autonomous drones and cybersecurity threat detection and response. One example is agents monitoring network traffic to identify and neutralize cyber threats. In education, agents can power personalized learning and virtual tutors that adapt content to student needs. Advanced agent systems are designed for complex and dynamic environments. Their value appears in situations that need collaboration, scalability, and rapid decision-making. 3 important approaches stand out here: swarm intelligence, multi-agent system architectures, and real-time agent systems. 0.2 is a key element in this context. 0.3 exemplifies these concepts in action. Simple agents cooperate to achieve complex goals. Swarm intelligence is inspired by natural systems such as ant colonies, bird flocks, and fish schools. These systems are decentralized, rely on local interactions, and produce emergent behavior, where larger patterns arise from simple rules. 2 named techniques are particle swarm optimization and ant colony optimization. Particle swarm optimization explores a solution space by adjusting positions according to individual and neighbor success. Ant colony optimization uses pheromone-like guidance. Applications include logistics route planning, drone coordination in robotics, and clustering or feature selection in data mining. Multi-agent system architectures define how agents are organized and how they interact. Hierarchical architectures place agents in layers and are easier to manage, but they are less scalable and can fail at a central point. Decentralized architectures support autonomy, scalability, and robustness, though they are harder to design and coordinate. Real-time agent systems are built for fast decisions in situations where delay matters. They emphasize low latency, adaptive behavior, and high throughput. Applications include high-frequency trading, autonomous vehicles handling navigation and obstacle avoidance, and healthcare decision support in critical care units, trading vehicles and care, and more. In e-commerce, agents improve personalized recommendations, dynamic pricing, and customer support. In financial trading, agents automate buy and sell decisions, assess portfolio risks, and monitor news or social media for market sentiment. Their effectiveness comes from efficiency and scalability, but privacy concerns, bias, volatility, and ethical trading remain challenges. 0.5, 0.4. In logistics and supply chain management, agents help optimize routes, predict inventory needs, and coordinate warehouse automation. Reported benefits include lower fuel use, reduced labor costs, faster delivery, and a smaller carbon footprint. At the same time, integration with legacy systems and disruption from pandemics or geopolitical change can limit performance. Agents in healthcare support diagnosis, patient monitoring, and epidemic simulation, while smart systems manage energy, lighting, and security. Large language models extend agent capabilities through decision-making, interactive communication, and data analysis. Their strengths include versatility, scalability, and adaptability, while bias, computational demands, and domain tuning remain concerns. Ethical concerns begin with privacy and fairness. Agents often process large volumes of sensitive data, so privacy breaches are a serious risk. Agents may also inherit or amplify bias from training data or programming. Source material recommends anonymization, encryption, regular audits, and careful review of training datasets and algorithms. Autonomous agents can make decisions that are difficult to explain, so transparency and accountability matter. Explainable models and decision logs can make reasoning easier to understand and review. Security is also essential because agents can face adversarial attacks or manipulation, which calls for robust cybersecurity, secure communication, intrusion detection, and related protections. Ethical decisions matter, which is why ethical frameworks should be built into decision-making processes. Environmental impact also matters because large-scale simulations can consume significant computational resources. The source recommends energy-efficient algorithms and green computing practices to reduce this cost. 02030405. Sensitive data should be encrypted and data collection minimized. Best practices bring these concerns into daily system design. Diverse training datasets and regular audits support bias mitigation. Explainable models and decision logs improve transparency, while robust cybersecurity protects agent interactions and ethical guidelines shape agent behavior. Ethical design often creates trade-offs with performance. More data can improve accuracy, but it can also weaken privacy. Greater autonomy can reduce human oversight and complicate accountability. Performance optimization can improve efficiency, yet it may also favor specific user groups and raise fairness concerns. Mitigation can include data auditing, algorithm testing, and fairness metrics such as demographic parity and equalized odds. A deeper ethical evaluation highlights bias from data, algorithms, and deployment in real-world settings. Regulation adds legal and policy structure through privacy rules, liability definitions, standards, restrictions, and ethics review boards. Improving agent-based systems starts with efficiency and scalability. The source recommends distributed architectures, parallel processing, dynamic resource allocation, and load balancing. It also points to lightweight communication protocols and more efficient reinforcement learning methods. These measures help address growing agent numbers, high computational load, and communication overhead. Future directions include hybrid systems that combine rule-based reasoning with machine learning, stronger human-agent collaboration, digital twins, decentralized finance, and explainable agents. Large language model integration can improve natural language processing, contextual understanding, and adaptability. Recommendations also stress cloud-based deployment, transparency features, and alignment with ethical and legal frameworks. 02, 03, 04, 05. When technical performance and ethical design are balanced, agent-based systems become more effective in the real world.